Okay. All right. So let's get going. Okay. So you guys have a quiz next week, and what I'd like to do to sort of guide you guys in terms of what you should know, okay, is that know all the reactions, on the back of the nitrogen chapter. So we didn't go over like reactions of the nitrogen-based molecules, but you should be able to rationalize many of them. You should expect to get questions that are kind of like, what's the product of this? What is the reagent to affect this transformation within the nitrogen chapter? You should know all of those. I'm not going to discuss them today, but I did put the video up. I do want you guys to know all the palladium catalyzed chemistry as well. I'm not going to quiz you on this upcoming quiz on the mechanism of that, but you should know the sort of like, what is the product of a Stille, what's the product of a Heck, what's the product of a Sonogashira. So you should be familiar with all the reactions that are in the transition metallized cross-coupling. So you should expect to get one question that's sort of like what's the product of this reaction, what's the reagent of this reaction that would be necessary to carry this out, and you will get one of those each from the nitrogen chapter, and you will get one of them from the cross-coupling / transition metallized carbon-carbon bond forming chapters. So hopefully that's a little bit of motivation just to get those up and going, and that'll probably be half of the quiz. The second half of the quiz is going to be somewhat of a, I don't want to call it a mechanism challenge, but we'll go over a little bit of it today, and it's one of the reactions that I like to have a little bit of fun with you guys, in part because it's a reaction that was important for me during my graduate career, and it's also, I think, cool because people that struggle with mechanisms, it provides, I think, a fresh start for some people that have struggled with mechanisms a bit to get what's, I think, conceptually a fairly easy reaction to wrap your head around with, which can then allow you to do some, I think, pretty cool modifications and things of that nature, and that's metathesis. So it's one of my, again, like I said, it's one of my favorites. And so yesterday, and I think we haven't been able to do this again today, I did this in office hours yesterday with some students to sort of introduce them to it, but I'll sort of redo this with everybody because I do think that this was something that was useful, and then we'll maybe step it up and try some more complicated ones, which may be sort of in line with the type of question that you'll get on the quiz, because I'm going to make them a little bit fancier than straight. I'm going to make them sort of not so straightforward, so you'll have to sort of figure it out on the quiz. But as you guys sort of know from, the sort of cycloaddition pericyclic reaction chapter, right? You cannot do 4 + 2s work thermally, 2 + 2s don't work thermally. If you sort of read ahead or talk, right, you can do that photochemically, you can do 2 + 2s, but at least thermally, you're not going to get 2 alkenes to form a, say for example, what's not going to happen is sort of a 2 + 2. So that's right. That's not going to happen thermally, right? So, but if you think about this, what the metathesis reaction is it's the use of metals to, in essence, affect this type of transformation. But not just this transformation. It's the 2 + 2, as well as the sort of retro 2 + 2 process, right? So the retro 2 from this would be we go back in the reverse direction as well. But again, neither of those is going to happen thermally. Now, but at least from a conceptual standpoint, thinking about this 2 + 2 retro 2 + 2 can, at the surface, help you see this. And so what an olefin metathesis reaction is, in essence, is it's a rearrangement of alkenes. Okay? So where can this become valuable? I'll get into where the metals come in a second, but I just want to sort of show this as an example. I have different colored chalk. That might be helpful here. I do not. So we'll just have to stick with R1, R2s. Now, if you had R1, say R2, and so we'll just do this to keep track. Right, we have 2 sets of alkenes here, right? Now you can imagine through a 2 retro 2 plus 2, you can start to get an actual switch of the partners, right? So if these react and they go through this 6-membered ring, or sorry, excuse me, back to things older. Again, this won't happen, but conceptually this can help you understand how cool the metathesis reaction is. Right, so we have the R2 and the R1 together, R3 and the R4. Now, we can draw the arrows that would go in the reverse direction, but we can also, depending upon how we draw this, we can also push arrows this way, right, which will allow us to, in fact, swap partners, if you will, right? So the R groups. So at least as I've drawn here, right, what you sort of see is that in the starting material, we have the R1 and the R2 together, the R3 and the R4, but through this 2 plus 2, retro 2 plus 2 that I've outlined, what you've done is you've in fact switched the partners. So R1 and R3 are together, R2 and R4 are not together. In addition, if we simply took this R2 and R1 and flipped it over and did the same thing, you can also imagine a mechanism where now you've got R1 and R4 and R2 and R3, right? Does everybody see that? So through a simple 2 plus 2 retro 2 plus 2 process, you really have a lot of versatility to completely reorganize ring systems. Now I told you that this doesn't work, right? This is not a thermally allowed process, which is why metals become important in this. And the metal that, well, metals, there's multiple metals, but the metal that has eventually come to be perhaps most widely used are things called Grubbs catalysts, which actually reminds me, today we have a speaker at 2, it's coming to us from Tufts, I believe, and the reason why I brought it up is his advisor worked with Bob Grubbs. His previous advisor with Bob Grubbs. So anyways, there's a talk today, look around for flyers. It's going to be organic based, so you might find it, well, some of you might find it interesting. But the catalyst, sort of Bob Grubbs is one of the sort of people that perhaps made some of the most thorough and perhaps most, I don't want to say practical advancements. It was sort of him and Richard Schrock were really the two people that sort of took some of the preliminary studies of metathesis and made it sort of practical. What was so special about what Bob Grubbs did was that he made a catalyst that was benchtop stable. You didn't have to use special, you could run it open to air. It was just very, very convenient to effect this transformation. And so you're not going to have to remember the reaction, but it's worth just drawing to show the relative complexity of the structure. So PCY. Somebody was asking me yesterday about abbreviations for cyclohexane. Who's asking me that? Somebody was asking me. Is it you, Saul? Cyclohexane? Cyclohexyl? Somebody was asking about cyclohexane. So usually you'll see it abbreviated PCY. CY is just an abbreviation for cyclohexyl. But this was one of the first. This is what's classically considered. These are cyclohexyls. This was one of the very first, I don't want to say one, there was other generations, this was the first one to sort of be given the name Grubbs catalyst, sort of Grubbs first generation catalyst. It works specifically for intramolecular metathesis reactions where, for example, you have two alkenes together. Subsequent advancements were made, and this was all taking place around the time when I was in graduate school, so this became a hot area where they sort of modified the group up here, which increased the activity. They got rid of this guy down here, increased stability. So again, I'm not going to get into the details of all of that. And I'm not even necessarily going to expect you to sort of know and draw this catalyst, but I just want to put it up there so that you recognize that there is other stuff to this molecule that gives it the activity. For the sake of this class, though, what we're going to abbreviate this for to help us out with the mechanisms and to just sort of simplify things is we will, in general, cut out all all the noise and refer to what is ultimately the important mechanistic component of this, which is the ruthenium carbon double bond that you see here. And so what we will do is we will abbreviate this sort of metathesis catalyst more generally for the sake of the mechanisms and so forth as just a ruthenium double bond to a carbon. So you got to recognize that there's a CH2 out there. Okay, does everybody get that? So now, what's special about the ruthenium carbene, if you want to call it that, or alkylidene, the ruthenium carbon double bond, is that this can actually promote a 2+2 retro 2+2. So if you had, say, for example, so I mentioned that this doesn't work. So this would just be an example of a cross metathesis, right? You can't do this. Can't do this overall process, but you can certainly imagine that that could be valuable, right, to sort of make substituted alkenes. Alkenes obviously are important. We've seen the importance of alkenes. But what the ruthenium carbene, or the ruthenium double bond to the carbon, can do is, because it's a metal, because it's not necessarily beholden to the same sort of molecular orbital theory that sort of carbon is, it can, in fact, do some of these transformations. And so what ends up happening is that the ruthenium alkylidene, and there's multiple ways you can do this, which makes it a little bit tricky, but you can, in fact, do a 2+2 with this molecule. And now instead of a 4-membered ring with carbons on it, right, now you have a 4-membered sort of molecule with ruthenium in there. And if you push your electrons, what can happen is you can, in essence, make the ruthenium alkylidene, which now bears the information from one of the alkenes, right? And now with the ruthenium alkylidene that can bear the information of one of the alkenes, now you can do the same retro, the 2+2 retro 2+2 with the other alkene. And what happens is you regenerate that sort of ruthenium alkylidene. So this is a class of reactions, I guess a broader class would be catalyst, right? You're regenerating the catalyst, and now the catalyst can re-enter the cycle, right? It can now react. Right, so now this can re-enter the cycle over here. And so one molecule of this ruthenium alkylidene can in principle do, thousands, tens of thousands, infinite number of cycles until eventually the metathesis catalyst might begin to decompose and go bad, right? So you can get lots and lots and lots and lots of turnovers, and people have found a lot of ways to get to extremely low catalyst loadings, to the point that, you might do multi-gram scale reactions with a single milligram of this ruthenium metathesis catalyst. Yeah, Africa. R2, R1, 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 R1. I brought in the R2 from over there. Yeah.
How can you control an experiment like this? Because then theoretically you could get it to add to R1 again and stuff like that.
Yeah. So ask me in about 10 minutes. Okay. Because what I want to do first, maybe 15 minutes. We'll come back to that at the end because I think it's a fantastic question. And it gets to different classes of metathesis reactions that you could have. So what I would like you guys, Sorry. 2 plus 2. Oh man. Okay, hold on. I'll shoot. Okay, for those of you that wrote it down, I'll just start you off with the question, and then for the rest of you, I'll just write the guide over there to sort of figure this out. But what I'd like you guys to do is, knowing the mechanism of the metathesis reaction, 1, 2, 3, 4, 5, 6, 7, 8, can you come up with a mechanism that explains what's considered a ring-closing metathesis, where you generate ethylene gas and this 6-membered ring. And again, just so that if you didn't write it down, what you have to remember, bless you, all that it's going to take to do this reaction is very straightforward. Is a series of reactions pushing them back and forth. So 2 plus 2, retro 2 plus 2. 2 plus 2, retro 2 plus 2. And if you do the 2 plus 2, retro 2 plus 2 on the sequence, you should be able to figure this out. So I want you guys to all try this out. And it's not as, again, I make it seem very, very simple, but what you begin to realize is because there's so many different ways that you can do this 2 plus 2, retro 2 plus 2, a lot of things can happen. This may get back to a certain extent what Nicole was asking, which we'll get back to later on. As it turns out, metathesis reactions are often generally driven by thermodynamics, but you can sort of force reactions in a forward direction based upon something like the gas. Like ethylene gas would leave the atmosphere, which would drive it in this direction. So, I'll give you guys about 5-10 minutes to try to figure this out. See what you guys come up with. Again, all that it takes is this. But if it was as simple as that, we wouldn't have you guys try it. I just want to have you guys try to work through it so you guys can hopefully see the answer. And for those of you that did this in my office yesterday, that might figure it out fairly quickly, I'll put up an even harder one. And we can return to a little bit later on, which is I'll say a harder one, but it introduces an alkyne into this system. But again, you're going to treat it in much the same way. 2 plus 2, retro 2 plus 2. And so if you get this one, you feel good about this one, try what's called enine metathesis next. And so again, this is the entry. This is going to represent sort of something that's variable enough from that I'm going to ask it on the quiz. So you guys will get something of this level of difficulty on the quiz. again, just keep in mind that the ruthenium, if you're obviously one of the first steps in this, right, is that the ruthenium is going to react with one of these alkenes, and that ruthenium can attack in one of two ways. One of which you will see as a productive pathway, the other way which you will see is non-productive. It doesn't mean that it can't happen. Sort of Nicole was bringing up previously, with all these possibilities, why is it going to go one way or another? And again, it's driven by ultimately what the product's going to be, either its lowest energy or sort of leaving ethylene as a gas. So the ruthenium sort of saying is that you can do the 2 plus 2 to ruthenium alkene in one of two ways. One way you will see basically just lead to your effect starting material. The other way will lead to an intermediate, productive intermediate, that then you can use to do the ratios. Does that make sense? To try to go through 2 plus 2 retro 2 plus 2 one way, and then if you don't see, I'd like you guys to see that on your own. So try it. So again, I've seen a lot of people put the ruthenium alkylidine reacting with the alkene in one direction, and what in general happens when they react it in one direction is they just regenerate the starting material. So you got to sort of reconsider the way in which case the ruthenium carbon double bond will approach the alkene. Okay, I don't want to give much more than that, but again, I want you guys to be able to see how just the two different approaches one will be productive, one will be non-productive, and there's nothing to stop it from going the non-productive pathway. It's just that eventually it will have to go the productive pathway in order for the reaction to, proceed. Yeah. Sorry, I missed retro. Well, there's only two options. You can swap. There's really 2 options. That's the thing about a lot of this, is there's 2 options for each step. When you do the 2 plus 2, there's 2 regioisomeric ways that you can make that cyclobutane. And then, depending upon the subsequent step, there's really 2 different directions in which the arrows can go. One place leads back to the starting material. The other way will proceed in a forward direction. Yeah. Try the alcohol. Let me see if you're. Right. So then just convince yourself. Oh, it looks like you did that. Remember? Yeah. So you saw that just led to, you rearranged the carbon, so if it was like C18, that would change. You're really just leading back to. Keep track of your electrons, keep track of your carbons. Yes. Right. And see how this way you basically just went back and started. Now you get everything you want. So now you can do the ratios. So you may want to read your water, closer so that you can sort of see it better. Because if you try to, do the 2 plus 2 from the other side, so you can use exactly. Yeah, you saw that's good. That's kind of what I want you guys. I was hoping that so you can see both ways and you can see that you can go this way. It's just not productive. All right, so I'm seeing a lot of progress on the first one. It seems like a lot of people are getting it. I'll give you guys a few more minutes, and then we'll maybe go through it together. Again, just 2 plus 2, retro 2 plus 2. If you find yourself doing things that are not a 2 plus 2 or a retro 2 plus 2, you're doing something wrong. Only a 2 plus 2 and a retro 2 plus 2. That's the only things that you need to do. If you find yourself doing something else, you're overcomplicating it. Yes. So what would the carbon do? Notice that this would be on the you're switching carbons, so this carbon actually you would literally go right up. There's no way to get to anything other than this if ruthenium's here. So now try to flip it with ruthenium. So the ruthenium, yeah, so that exactly. Yeah. So try that. Okay, so I'll just give you guys a hint really quickly, and then give you guys a little bit more time to try to figure out on your own. A lot of you guys started, I think, going this way, right? Where you get a 2 plus 2, where the ruthenium, and that would make sense, right? I mean, we've seen, oftentimes when we've seen things where they're sterics, right? We might make the assumption that the bigger group would be sort of away from the sterics. So I think intuitively, it would make sense for you guys to think that what might happen first, if you're going to do 2 plus 2, is that the ruthenium is going to end up here. But what you find is that when the ruthenium's out at this position, if you do the 2 plus 2, retro 2 plus 2, no matter how you do it, you're going to get back to a ruthenium alkylidine and the same alkene. Now, you might switch 2 of the carbons, right? So the carbon that's here might end up here, right? But you're still going to get back to what's essentially the same starting material. So if this is what you've been doing and you get stuck because you can't see anything, switch it up, rotate the ruthenium around, and start with it there. Okay, so try to do the 2 plus 2, retro 2 plus 2 with the ruthenium towards the more sterically encumbered site, and then see if you can get to the product from there. And I've seen a few people get this one as well. So, trying to think of another tough one. So if you've gotten this one and you're just sort of sitting there, you can take out other stuff and study it. But another thing that you can do is just play around with multi-ene or alkyne molecules, draw a few molecules, and just try to predict what would form from those. So just get a little creative and try to propose your own, maybe try to put 3 alkenes in a molecule and think about what that would make. Try to put, and there's lots of options. So just play around with it to sort of see what you could make from these. You just pick 1 alkyne, 2 alkenes, just play around with possibilities if you've got those 2. No, you didn't. You didn't. Yeah, but you can also flip this. No, see how your alkene here is pointing down, your alkene here is pointing up? So you basically flip the bolt, so you were the same predicament. Alright, anybody? Yeah, so now the key is, right, so now the key is when you're trying to here, but try to make it, you know, it's tough to see in that way. You want to get it like parallel to each other, right? And then build the rest of the molecule around. Does that make sense? If you're sort of twisting everything, it's going to be a little bit. Oh. So you yeah, you just got to be more clear. You need to generate. Oh, I use that. So, oh, you just scribble out. Oh, got it. Actually, come on. Okay, so you don't and it's going to be kind of broad. Okay, so I just want to take you guys through the first part of it. So I think where a lot of people are struggling now is on. So I think people are, for the most part, are getting the first part. And if you can't, I'll just walk you through it here, right? So we discussed that the ruthenium's on the other side. Now, a lot of what was happening is you guys were taking me quite literally on the placement of this ruthenium, but remember, it's going to be based upon the relationship of this. So if this is, it's about, in essence, it's about the ruthenium ultimately ending up on that carbon. If the ruthenium's out there, you're going to regenerate the other one. So that's why you wanted to go this way. You're going to do a 2 plus 2. Okay? And now at this position, like I said, so each case you have 2 options. So you've got 2 options for the 2 plus 2 that generates the ring, which we saw the one case, there's no way to get to the product if you go the one way. If you go the other way, the first step, at least you get your carbon in the right position. But if you fragmented this way, you'd literally be just going right back to the starting material. So even at the 2 plus 2, the retro 2 plus 2, there's 2 alternative ways. So you can go this way, or you just rotate over, right? And you go that way, right? And when you do that, now what you get is you get your ethylene, right? And your ruthenium is now on the alkene. Okay? Now, the tough part, and what I noticed is that people that seem to get this were really good at recognizing that they needed to redraw the molecule, right, in a more suggestive way, right? If you're trying to see, you want to see another 2 plus 2 retro 2 plus 2, but, you know, we see it here, you know, with them kind of parallel to one another, where they're in close proximity. Now we've got the alkene out over there. Do I have the right number? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Yeah, so 1 extra carbon. So now what you need to do is you want to kind of redraw this in a way that might be a little bit easier to see the 2 plus 2 and form that 6-membered ring. Okay? So what you should try to do at this point is this is a time when you might want to redraw the molecule. You kind of know what the product's going to look like, right? You know that it's going to be a 6-membered ring, 1, 2, 3, 4, 5, 6, and then you know that you're going to be doing it 2 plus 2. So what you can start by doing is thinking about that 6-membered ring, maybe draw that 6-membered ring to sort of help guide you, and put the molecules in the right position. Right? But ultimately what we're going to do here, right, is is you've got your ruthenium alkylidine there. So basically when I rotate around, you can count your carbons, because again, when you're making rings and stuff like that, a lot of times you can run into problems, and I was even looking at Jessica's earlier, and she had the right answer, and I was like, it's wrong. So I can miss-see these as well, even though she was right. And so this is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? And now we've positioned ourselves so it's going to be a little bit easier to see the 2 plus 2 retro 2 plus 2. So this is an important lesson on making sure that you can redraw them on again. Because they're the same molecule. I just redrew it. I mean, you can use just something that says redraw or whatever. But I didn't want to show like a reaction arrow or something like that. Oh, I'm sorry. Yeah. All right. How should we? Huh?
You put in parentheses?
Maybe I'll do this kind of arrow. Right, that's that. Yeah, but that's a good point, is that we've had all these alkenes, and so the equal sign might be confused with an alkene, so that's a good point. So, yeah, so, oh, you know what people will do sometimes is, that's why people do this. They'll do 3 lines to show equal. That's why people often use that. That's probably why people often use it. But then again, if you have a triple bond, you can use it. This is this, redrawn. But thank you, because I now totally appreciate how confusing that can be. This is this redrawn, okay? And now that we're at this molecule, right, we can do our 2 plus 2. It's a little bit easier to see. Right, so now we've made our 6-membered ring. We're going to do our retro 2 plus 2. We're going to generate this, and we're going to regenerate our ruthenium alkylidine. Okay, so does everybody see that? So this is one of the reasons why I like this, is it does take some redrawing. It does take a lot of the skills that you need to be able to develop in a mechanism problem, but at least it simplifies it a little bit by knowing that all that you have to do is 2 plus 2, retro 2 plus 2. 2 plus 2, retro 2 plus 2. So again, this is one of the reasons why I like this one. It does help people that may have struggled with mechanisms previously to basically say, hey, listen, when you see this, it's going to take it's a bit of a maze. You got to figure out how to get there, but it sort of simplifies specifically what the mechanism is. So you only have certain arrows that you have to worry about. So if you master this, you can play around with mechanisms and try to get there. Okay, so let's try the next one. And we'll go through this one as a class because I saw a few people get this. Okay. And so this is a type of metathesis reaction. It's called an enine metathesis. Why is it called an enine metathesis? Because it's an alkene and an alkyne, right? So enine metathesis. And the product is this molecule here. And again, there's multiple ways that we could go about drawing this. And in fact, there's probably 2 ways that you could do it that could lead to product in this case. But the key here is to not deviate from the 2 plus 2 retro 2 plus 2. I saw a few people that had gotten this one and were trying it, and they get to an intermediate that looked just slightly different. And so they started to try to do things that weren't 2 plus 2 or retro 2 plus 2, which you don't need to. That's what I'm sort of telling you guys. I'm trying to simplify this for you guys. It's 2 plus 2, retro 2 plus 2, and within that mechanism, you can do a lot of really cool things, right? So, okay, so now we're going to put our ruthenium alkylidine, and we're going to go 2 plus 2 retro 2 plus 2 with one of these. If we do it with the ethylene gas, what's going to happen? Yeah, you're just going to recreate the starting material. So if you go ahead and you try to do the 2 plus 2 retro 2 plus 2 with this, if that's where you start, it's okay. You had some practice doing 2 plus 2 retro 2 plus 2. As long as you don't screw something up, you should see that you are back to the starting materials. Okay? And it turns out, for enine metathesis, there is a right way that the metathesis goes. But at least for this problem, you don't have to worry about that much because it's a little bit more of a simplified version. So whether ruthenium goes one way or another, we can get to the products in either way. Now, I saw a lot of people go this way, which turns out to be not the way that the reaction goes, but that's totally fine. Doesn't matter at this point. I think the reason why people went this way was because they wanted it closer to the R group, which is what we've seen with the ring-closing test. It's totally logical, and it turns out for the sake of this mechanism, it doesn't matter, at least at this stage. Okay, now follow with me. So we're going to do 2 plus 2 of this molecule. So go ahead and, if you haven't gotten to this one yet, try to preempt me. Draw what you think the 2 plus 2 is going to be from this. We're going to generate our 4-membered ring with our ruthenium here, but there's going to be one big difference. Right, we had a triple bond, and so now when we do this chemistry here, we'll still have a double bond remaining. Does everybody see that? All right, it's the same thing, again, with the, good example was the Diels-Alders with alkynes, or the hexadehydro-Diels-Alder in the exam. And now that we're here, right, we want to do our retro 2 plus 2 again. Now, again, if we did this, what's that going to do? It's going to go back. So those are the arrows that would go back to the starting material. So you got to just rearrange the other bonds. So you got to go this way. Okay. So what's going to be the product if I do that? 2 plus 2. So go ahead and try to draw what the product of this is going to be before I do. Right? Well, we're going to have a double bond there, which is now going to become a single bond. We're going to have a double bond there, and we're going to have a double bond there. And so the product that we're going to generate is going to be that molecule there, which is starting to look a heck of a lot like the starting material. I'm sorry, the product that we've drawn, right? So we're very, very close to here. And now at this step, what do you think we do? We've got to bring in another alkene. We haven't introduced this guy yet, right? So now this is probably a pretty good time to introduce the alkene. Okay, so there's our 2 plus 2 again. Now you can do a retro 2 plus 2. One of these retro 2 plus 2s will, as always, lead back to the starting material. So you got to pick the 2 plus 2 that's going to go in a forward direction, and that's going to be this one, which you should see leads to that and regenerates our ruthenium alkylate. Okay? All right. So hopefully you guys kind of see that, again, this is kind of cool bond rearrangements can take place with the metathesis reaction. And it doesn't take anything overly fancy. We just have specified things that we need to do. 2 plus 2, retro 2 plus 2, 2 plus 2, retro 2 plus 2. So you guys can all expect to get a question on the quiz that is going to be something like this. It's not going to be anything that you've ever seen before. I don't think it will be anything that you've ever seen before. But it will be solvable using 2 plus 2, retro 2 plus 2. So you want to try one more together, or so we'll try one more together. And then maybe we'll move on to some other questions. Okay, so so as I sort of mentioned, metathesis, I think one of the reasons why I have metathesis is one of these reactions that I enjoy a lot is, again, because from a pedagogical standpoint of a simplified, fairly simple mechanism that I think a lot of people can sort of grasp and then kind of do some cool bond reorganizations. I do like that component. But it's also because, again, I spent a lot of time during my PhD work on the metathesis reaction. And my advisor at Boston College, one of his big contributions early on, that again he made early on when metathesis was really starting to become transitioned to sort of synthetic organic chemistry. So a lot of the early work of metathesis was in material science. So it was actually DuPont where a lot of the early work was made, and it was based upon polymer chemistry. So people would find, they basically discovered that they were getting these interesting polymers that they could only explain through these 2+2 retro 2+2 mechanisms. And then over time, as they began to understand it more and they began to have more control over it, it began to take root in sort of total synthesis, so multi-step synthesis. And so it's become an extremely powerful reaction in total synthesis. And there's a lot of different things that you can do. Again, I showed you E9 metathesis, ring closing metathesis was one of the first ones. Nicole was asking about cross metathesis kind of earlier in terms of dimeric molecules, and if we have time, I'll get into that as well. But let me tell you what one of the things that that my advisor did. Now, it turns out that if you take highly strained alkenes, such as the one that you see here, I want to show you the mechanism, and then maybe after this I'll give you some background in terms of the historical context and why this was important. Maybe I can throw in a. You know what? No, I'll show you the original stuff. So, as I sort of mentioned, the metathesis reaction early on in the early development of it was sort of towards polymers, and we're going to be getting to polymers next week, right? Polymers are basically repeating units where basically you set off cascade processes that continue basically the same reaction over and over and over and over and over and over and over again. Okay? And within the metathesis reaction, one of the polymers that you would get would basically be, so I'll just show you guys. It's a polymer, so it's difficult. I'm trying to think of where to stop in this. Let's do this. We'll take you through one cycle with the ruthenium catalyst, and we'll get here, and then hopefully it'll explain. So, let's all try to show this mechanism. So this is the beginning, in essence, of a what's called ring open metathesis polymerization reaction. Okay, and so as you can see, there are two equivalents of this in the molecule, and I sort of left the ruthenium alkylate on there. So you should be able to draw a mechanism where this is eventually converted to this. So why don't we spend a little bit of time trying to figure that out? And again, this is the type of question that I might ask on the quiz. So again, 2+2 retro 2+2 is all you gotta do. Yeah. Here? No. Oh yeah, sorry, yes, thank you. Now it's like a question you'll get up. So I think cis is synthetic. Generally, it's not the most cis translation, but so you'll likely get a mixture of polymer, some cis, some trans. Because of the fact that it's reversible, in some cases you can actually drive trans say for example, by running from the ethylene or something like that. So it's a reversible nature of trans, but you do get a mixture of cis. That's a good point. I'll bring it. Don't worry about the cis-trans nature of the alkene. At this point, it turns out that it is slightly cis-selective, but we're not going to worry about that much at this point. You can also make it trans-selective by sort of allowing it to equilibrate with trans. Okay, and so if you get this, which a few people have now, what my advisor did was he showed that if you do this reaction in the presence of alkenes, actually I think he got cis. Again, the cis-trans doesn't matter for this, but I'll just to be accurate, he was getting mostly cis for his stuff, so. Say it again? So it's a ruthenium alkylidene, just like up here. That is an R. That is from this. Yeah. So if you've gotten the polymerization one, try to now figure out the sort of cross paths. Yeah, so yes, it's no. It's the top is ring open metathesis polymerization. The bottom is ring open cross. That's RU1. Yeah, this is R. Yes, you can look at it. So now, don't worry about this. All right, sorry. I think I just gave a lot of confusion on this. There's a lot of confusion that I just, you know what? This is a different problem entirely down here. Yeah. Completely different problem. A lot of people are like, wait, you shown the answer? No, this is a completely different product. I just saw that some people had gotten the top one right. So this is ring open metathesis polymerization. This is one of my advisor in grad school's major contributions to metathesis, which was a ring open cross metathesis. So it's a similar mechanism, but it's it was I can have to find. He basically using this, he took molecules that took like 15 steps to make, and he was able to use this to make it in like 2 steps. Kind of cool. In other words, this we have drawn. Yeah. Right. This is not hard to see. Yeah, try to connect. How many parts together?
So now that you made the product, right? Are you the ones reacting to their
So the reason why this is because it's strained. This is much more reactive.
Yeah, but still now you have that problem in the presence of that.
He uses okay. I'm gonna because this kind of gets to what Nicole was talking about earlier.
Yeah, that's the agreement. It's like I need someone who always started
Let me clear
I need someone who started That's my number one question.
Yes.
Oh yeah, actually, same note.
Alright, so we've got about 15 minutes left, and I just want to prep you guys for next class. Spend a little bit of time, but I'll just go through this one really quickly. I'm seeing a lot of progress here, and I just want to get to answering Nicole's question before I move on. So what you're going to do here is obviously there's two of these, right? And so when you do the 2 plus 2, you're going to get to that molecule there, and now what do? We're going to 2 plus 2, right? It doesn't because it's symmetric. In this case, this is a symmetric molecule, so whether it goes one way or the other way, you're going to be the same thing. Now, what some people are doing here, and I might as well sort of mention it quickly, some people will now, and I'll just sort of nip this in the bud here because, you know, it's unnecessary, but I kind of see where it's coming. A lot of people are trying to now introduce a second ruthenium alkylidene. You don't need to do this at this point, right? So I would try to treat this, you know, maybe there's cases where that would be the case, but in general, it's not something that you see. So if that ruthenium alkylidene, until you regenerate, say for example, ruthenium alkylidene, you don't have to bring it back into the system, okay? Now, what's going to happen with this? It's going to react with another equivalent. Again, it doesn't matter which way we go because they're both the same. We're going to do retro 2 plus 2. Okay, you're going to get to that molecule there, which again, you got a lot to keep track of, but you just follow the electrons. You know, it's a lot to keep track of because there's a lot of carbons in this, but in terms of the electrons, it's not that different, so you just got to make sure that you don't make mistakes as you're redrawing it, which can happen. right? And then you're going to do the retro 2 plus 2, and that's going to get you there. Okay, so because it's been asked, and then again, try to bring open cross metathesis on your own. So one of the questions that came up is, because all these things can happen, how do you drive a reaction one way or another? Now, certainly, as we sort of mentioned, ethylene gas can certainly be used to drive a reaction. It can also render the reaction reversible if you run reactions that are ethylene. So, for example, a lot of cross metatheses are cis-selective, but if you do them in the presence of ethylene gas, it renders it reversible to the point that you ultimately get trans. But usually when you see cross metatheses, can I ask you to close those doors? She just went to tell them that. Okay. Thank you. Okay, so what we really refer to there primarily, so we had a few different things here, right? We had ring closing metathesis, we had ring opening cross metathesis, we had E9 metathesis, but a standard one is simply cross metathesis, right? Which was kind of what we were reflecting in the early part. And so you can certainly imagine that if you have molecules like this, if you just have 2 alkenes, right, and you were to do a cross metathesis, you could in principle get up to 3 different molecules, right, that would be the products. And that's not including cis-trans isomers. Just alkenes themselves, you can get really 3 sets, right? You can get 2 homodimers. I'll just draw them as cis for now. So the 2 homodimers. And the heterodimers. Right? So the R1 alkenes can react with one another and dimerize. Or you can couple the R1 and the R2. Now, based upon your knowledge of chemistry, there's one, if you really wanted a coupling and you really wanted to maximize the amount of this that you would get, what might be a trick that you could use to, maybe let's see if you did that. Think about that, I'm going to do it. Alright, so, now that we can hear, how might we do, and keep this in mind, right, because if you guys are out there before another class, it echoes in here, so just be respectful. Anybody have any ideas of how we might force this product to be the major product?
It's R2 and R2. One of the products.
Oh, sorry, yeah, good catch, thank you. Yeah, so if we wanted the coupling, and again, I'm not saying we have to limit one or the other, but what would be one way that we could maximize this? Protecting group's not necessarily going to work. This is a tough. I guess I'm asking you guys. I'm sort of asking you guys to read my mind. So this is. So you're kind of getting to a second point that I haven't really given you guys the information to answer. I was more just going with the Le Chatelier's principle, right? And this would be based upon if, say, for example, R1 was something really valuable. If this alkene was really expensive and really valuable, and this one was cheap, right? You could throw excess of this at there. You get a whole bunch of this, but you get very little of this, right? So at least you can maximize the production of this, and you wouldn't be wasting perhaps precious material. And so this is something that's actually done fairly commonly in cross metathesis, is that you take the cheaper alkene, usually maybe one alkene took you several steps to make, and then you have maybe a commercially available alkene that you're going to try to couple on there, so you just use an excess of that other guy, and then you can sort of force it in the forward direction. But there are other ways which sort of alluded to, Jonathan, were you bringing this up? Did you say sterics? No, it was Chaim brought up sterics. So Sterics doesn't necessarily work that great with this because if you just have sterics, right, you're probably just going to get a whole bunch of homocoupling of the less sterically one. And so what you actually plan, again, you're not responsible for this, but I figured I would mention it, is that there's electronic differences between these that you can actually take advantage of. And so one of the really interesting things about the metathesis reaction is that you get this situation where if you have, say for example, an electron withdrawing group on here, right? Hopefully I get this right. It's been a while since I thought about this. I believe, I knew this a year ago. I think, and so you'll get the general, you're not responsible for this, but you'll get the general idea whether it might be the inverse of this, I might be wrong on this. But if you have an electron withdrawing alkene, I think that the way that it works is that the ruthenium alkylidine is actually faster to react with this guy here. Is this right? And so again, if you do the 2 + 2, retro 2 + 2, you'll get this guy here. And then, where's the slower? I forget the details of it. But I think it's faster to react with this one, it's slower to react with this one, but then this one's more reactive. So like, you can like slowly add this one into the reaction solution, you sort of gear it, whatever. There's electronic ways that we can do them. So the two different ruthenium alkylidines are electronically different. There are different rates that each of them can go through. Bob Grubbs wrote a review on this back in like 2002, I think, or 2005, where he sort of described these. But there is an electronic preference where if you have an electronically rich with electronically poor, based upon the relative rates and reactivities of the molecules, you can actually force it to go one way or another. So that's not the best answer in the world, but at least it gives you a general sense that there are differences. You're not responsible for them, but there are ways that people have come up with this to actually do this chemistry. Okay, so we've got 5 minutes. I just want to do a quick introduction to what you're going to be responsible. Now, you're not going to be responsible for these mechanisms on the quiz, but you will. Metathesis, yes. You will all get a question on a metathesis mechanism on the quiz. You will not be responsible for mechanisms on cross-coupling chemistry, but we're going to spend all next class on cross-coupling. So I just want to sort of give you guys a very general overview so that you kind of know how to sort of compartmentalize cross-couplings together. So you guys learned previously, right, that, for example, if you take a Gilman, right, if you take like a Gilman, right, and you treat this with a alkyl halide, what's the product of that? You get basically right. So you get a carbon-carbon coupling reaction, right? So you basically make the carbon-carbon bond. Now, the thing with this, right, is that you're sort of relying upon stoichiometric amounts of cuprates. The way that you make these cuprates is you have to make the alkyl lithiums from them, which can often be pyrophoric and are difficult to handle, so it's not necessarily something you can order. Well, you can order them, but they're somewhat difficult to work with. But it turns out that if you take, there's a variety of different metals that are much more stable. Things like tin, things like, it's not really a metal per se, but it behaves in this way. Boronates, boronic acids, zirconocene, so zirconium-based metals, and Grignard-based metals. You can do this same reaction, but you need a catalyst. And the catalyst that is universally employed or most commonly associated with this reaction is palladium. Okay? Now, palladium, what we're going to get into here a little bit, which we haven't dealt with in the past, but this is why I wanted to just sort of get you guys sort of recognizing this, is that the palladium catalysts will go back and forth between sort of different oxidation states. So there'll be the shuffling of oxidation states, oftentimes between 0 and 2. So usually I like to show it as 0, it's a catalyst. And what will happen is that And this is going to be, you'll sort of see this as being fairly consistent among a lot of the mechanisms. I haven't used the board space the best here. What ends up happening here is that the palladium, remember how Grignards, we generated like Grignards where you basically take magnesium 0 and you treat it with an alkyl bromide and you generate a magnesium, sort of, it's almost like the magnesium is 2. That's kind of like what the palladium does in this case. So the palladium inserts itself within the alkyl bromide. Okay? At this stage, and this is the key step that's going to be new to you guys. So this is going to be fairly similar to Grignards. You can sort of rationalize it within Grignards. But the key difference and the key sort of new reaction that's going to be relative to all these reactions is something called a transmetallation. So what can happen is when you have alkyl groups that have metals on them, you can perform a process that's sort of considered a transmetallation. And what that means is that basically the palladium will, in essence, switch itself with the sort of the metal that you have here. You can often think about, they often consider these nucleophiles, so you can sometimes think about it as this group reacting and displacing the bromide, for example. But what happens here is you generate you sort of, again, it's sort of transmetallation, that's what it's called, it's transmetallation. So what happens is you can imagine this, mechanistically it's a little more complicated, but you can imagine the R group attacking and leaving the bromide, for example, at the palladium. This is often referred to as your nucleophile, and this is often referred to as your electrophile, so you can sort of imagine that. And then what happens here is a process that's called a reductive elimination. And so you go to palladium 0, and it basically snaps together the R1 and the R2. And you regenerate your palladium 0, okay? So, again, I go through this, yeah.
So it's R2 and R1, not R1 and R1.
Oh my god, yeah, I'm just wonderful today. Yeah, so R2 and R1, so it's a cross coupling. And so you have control over this, and you can often get away with one equivalent of this, one equivalent of this, very powerful carbon-carbon bond forming reaction. So this is going to be the basis, and so watch my video if you haven't already. We go through this a little bit more in depth, and we'll spend some time on Monday, I assume that's your next class, going over this. Okay? All right.